Welcome to my talk, The Power of Function Composition. My name's Conor Hoekstra. I go by code_report online, and we're going to skip over this pretty quickly. This is a summary of and about me. The key highlights here are that professionally I've developed in C++ and Python for, I guess, almost over a decade now. And over the last 5 years, I've fallen in love with the array languages. If you were at my workshop yesterday, you will already have seen a lot of these languages, and today is going to be a more polished version, hopefully, of what the folks in the workshop saw yesterday. It was mentioned in the introduction that I have 4 podcasts because I guess I love talking a lot. The middle 2 are the ones that are relevant to the content that I'll be talking about today. Arraycast is a podcast that I actually have with a fellow speaker. He's a panelist, Stephen Taylor. He had a great talk. If you didn't see it at this conference, I recommend you catch it online. That talks about all of the languages you're going to hear about today, but I also have another podcast that focuses on tacit programming and point-free programming. The most popular one, though, is the one on the left, Algorithms, Data Structures, and Programs. I might, this evening, be going around and interviewing attendees and speakers, so if you want to be on this podcast, come and find me, and you can say hi and tell me what you thought about the conference and the talks. And that one primarily focuses on C++ and systems languages, but we talk about a variety of different things, so... The other thing I thought is worth mentioning, because I don't usually do a good job at conferences of highlighting this, is I also have a YouTube channel, goes under code_report, and specifically relevant to this conference, I did a poll yesterday in the workshop of what languages people were developing in, and by far, Scala was the number 1 language. So my 4th most popular talk of all time is called Functional versus Array Programming, and in that talk, I go through a single problem, and I solve it in Scala, Haskell, and APL, and then I think BQN at the end. So if you're interested in this kind of stuff and you want to see, a Scala example, we're not going to see Scala today, maybe go check that out online afterwards. Everything I just mentioned, podcasts, YouTube, all my talks that I've given previously can be found at this GitHub repository, and that is going to bring us to not the start of the talk, but actually a little bonus. So I inserted this in the last 24 hours. Does anybody know what this BQN code does? If you were in Chris's The Butcher Bird Combinator talk yesterday, the opening keynote, it is the equivalent of the code that he showed at the beginning, where it generates you 1 1s, 2 2s, 3 3s, up to 7 7s. And I thought it was brilliant when I saw this piece of code. One, because I knew instantly that I could solve this in BQN with like 3 characters. But 2, because in this code that Chris shows, there is a spelled out combinator, which is the lambda fun bracket n, n bracket, paren repeat nn. Here you're taking a binary function repeat, and you're passing the same argument twice. That is what's known as the duplicator from the old school combinatory logic. It's known as join in Haskell, and it's known as self in the array languages. It goes by a couple different names. And so just in case you want to parse this, so this is range. It's the exact same thing, basically. Gives you a sequence, in this case, from 0 to n minus 1. This is repeat. And then this little squiggly up, the superscript tilde, that's the combinator that duplicates the argument and passes it. So it turns this binary function, which takes basically a list of integers, in this case 1, 2, 3, 4, 5, 6, 7, and then it replicates the integers on the left by that many times, which is exactly what we want to do in this case. You want 1 1, 2 2s, 3 3s, so the list of copies that you want is the same as the values that you're copying. So this makes use, this is called the W combinator from SKI combinator calculus, and also implicitly here is the B combinator. So 3 beautiful symbols, that is the equivalent. And I think actually we're going to do some live coding, and the first live coding you can see, this is an online editor called BQNPad, and this basically, you can see, is doing, so if we get rid of these 2, this is just the range that gives you 0 to 6, and then if we do replicate and this, it generates you this. And you can obviously, not do that. We need to leave that there. If we come over here, we can change this to 4, 6, to prove that, I'm not just making this up. So that was our first live coding. We're going to go back to the slide deck. That's just a little bonus and a taster for what this talk is about. It's about these combinators that allow you to write this extremely terse but also extremely expressive code. So the main thing we're going to focus on in this talk is function composition. I'm sure all of you at a functional conference, you know what this is. Primarily the type of function composition that folks do, though, is composing unary functions together. However, there's way more than just unary function composition. And on top of composing functions, there are different strategies for composing functions. And we're going to go over a number of these strategies. So most of you are going to be familiar with operators and functions, but the final three, trains, chains, and stacks, are three different ways of composing functions that you only have access to in array languages. Not that you couldn't do it in a functional language, but primarily that's where you'll see these. And so this slide coming up next is the main takeaway. If you only take away one thing from this talk, it's that across these different languages, there are a plethora. There are many ways of composing functions. And I'm about to highlight them. So everything in blue, that's a function, when you're composing functions with functions. Then everything in green, these are what I call trains. And we're going to talk about them when we get to it. It's the juxtaposing, the putting just side by side of functions. There are things called two trains where you put two functions next to each other, and there are things called three trains. You just saw a two train. The slash tilde is one function, and the range is another. Just by putting those next to each other, you get unary function composition, the B combinator. Up next is chains. This only exists in a language called Jelly, which is a code golfing language. It was designed solely for the purpose of winning code golfing challenges. But inside this language is an extremely interesting idea of composition through chains. And then last but not least, we're going to look at Uiua, which is the combination of a stack and an array languages. All of these languages outside of APL was created in the 60s, J was in the 90s, Haskell, I think, was early 90s, late 80s. But all the other languages are relatively new. BQN and CAP were both invented in 2020. Uiua was invented in 2023, and I think Jelly was invented in 2016, and they've been developed since then. So if you haven't heard of some of these languages, don't worry. A lot of them are really, really new. So the next thing we're going to talk about is up in the top left-hand corner, we have this FOF. And FOF stands for function-only function, which is a type of combinator. So before we start looking at different types of combinators and what is a combinator, we're going to look at these different definitions. We're going to go through this quickly. So if you don't pick up on all this, you can go back, watch the YouTube video, and slow me down to 0.75 times speed. But I just want to get some definitions out of the way. So the first thing is that we've got combinators versus pure functions. A combinator, specifically, is just a function that refers only to its arguments and nothing else. That's the simple definition of a combinator. So you can't refer to some global state. You can't refer to a constant defined inside the function. The only thing you refer to is the arguments. That's what a combinator is. The first time I learned this, I thought, is that the same thing as a pure function? It's not really. You can come up with examples. Technically, a pure function could be a function that defines a constant inside, but then you're no longer referring just to the arguments. So there are examples, so they're not exactly the same thing. The next thing I thought was, these both sound kind of similar to a higher order function. But that's also not the same thing. You can come up with examples of pure functions and combinators that are higher order functions, but also some that aren't. But I have a mental model that looks like this. Now, they say all models are wrong, but some are useful. I find this mental model incredibly useful. So if we assume that all functions are pure functions, then higher order functions and combinators are both examples of pure functions. So the question is where do the combinators that I'm talking about in this talk fit in this Venn diagram? Is it this green circle, or is it the overlap of the green and yellow? The answer is, it's almost this blue circle. Technically, a couple of the combinators that I'm going to talk about don't fit inside this yellow and green. And so when I say combinator, I'm specifically referring to these combinators from the SKI combinator calculus. And specifically, K and I are the ones that are outside of this, because K and I, when we see, don't need to take functions. So really the ones that I want are the ones that intersect blue, yellow, and green. And this is what I call function-only functions. So function-only functions are functions that are combinators, so they only refer to their arguments, and all of their arguments are functions, as well as the thing that you return from the function. So really, it's just a function that the only thing it deals in is functions. And you can think of the B combinator, unary function composition, which we'll see in a second, is just composing two unary functions and returning you another unary function. So all of the languages, Scala, Haskell, that you're probably familiar with, Clojure, have facilities for doing this kind of thing. So this sort of gets all this out of the way, and technically there's no such thing as the intersection of yellow, blue, and green that's not also pink, but I didn't have the energy to go and like make some, fancy shape, so we stuck with this pink circle here. So to recap, these are all the definitions, and the main thing that I'm going to be talking about in this talk are SKI combinators from the combinator calculus or combinatory logic, and specifically these function-only functions that deal only in functions. So the next part of this talk, what are combinators? Let's see some examples of these combinators. So the elementary combinators were introduced in a 1958 textbook by Haskell Curry. You might have all heard of this individual. The Haskell comes from Haskell Curry, and currying also comes from Haskell Curry. He, for 3 decades, his main research was on combinatory logic. He published his seminal text in 1958 with Robert Fays, and I believe in chapter 5, he introduces the 5 elementary combinators. And they are I, the elementary identificator, C, the elementary permuter, W, the elementary duplicator. That's the one we saw in the first example. It duplicates your argument and turns a binary function into a unary function. B, the elementary compositor, and K, the elementary cancellator. So we're going to go through these one by one plus S. So the first one, I. This is Python syntax. I chose Python for no reason other than most folks, even if they're not Python developers, can read Python syntax. So it's like the lingua franca that everyone can understand. The I combinator, aka id in Haskell, or identity, just returns you what you give it. So this technically isn't a function-only function, because you could give this the value 42 and it'll return you 42. But you can also give this a function and it'll return you that function. Doesn't seem very useful, but it comes in handy once you start to use this stuff. Next up is the K combinator. This is known as the elementary cancellator, and you can see why. You're given 2 arguments, and then it discards the second argument. So very similar to I, but instead of taking 1 argument, it takes 2, and it gets rid of the second one. Up next is W. This is the one that we saw. It's given, so this is a function-only function. F is a binary function, and it returns you a unary function that just passes that same single argument twice to the binary function. Pretty straightforward, but we saw in the first example how we can utilize this to avoid having to state our arguments, which is the whole point of tacit and point-free programming. We want to avoid our arguments. So I've been mentioning binary, unary, and for clarification, here's a little digression. It is very confusing that in array languages, we refer to unary and binary functions, aka functions that take a single argument and take 2 arguments. They refer to them as monadic functions and dyadic functions. So when you hear me say monadic, it's nothing to do with monads. And this comes from Latin and Greek. So Latin uses unary, binary, and Greek uses monadic and dyadic. And there's actually ones for ternary, triadic, and quaternary, and tetradic. You're not going to hear me say that. But if you ever hear me going back and forth between unary, binary, and monadic, dyadic, that's what I'm referring to, just the number of arguments that the function takes. So end of digression, and back to the W combinator. So F, a binary function that returns you a unary function. Next up is B. So this is probably the most common combinator. It's unary function composition. B is a binary function that takes 2 unary functions as arguments, F and G, and it just applies G first and then F. So this is a unary yielding binary function that takes 2 unary functions as its arguments. So a lot going on here, but it's really quite simple. Next up is the C combinator. So this is known as flip in Haskell. It takes a binary function and returns you a binary function and just flips the arguments that you're passing to it. So for commutative functions like plus and multiplies, this does absolutely nothing because it doesn't matter the order that you pass your arguments. But for non-commutative operations like division or minus, this can become really, really useful. And last but not least is the S combinator. If you're familiar with combinatory logic or the SKI combinator calculus, you will have heard of the S, K, and I. We saw K and I already, but S is the third and one of the most fundamental combinators in terms of having a Turing-complete calculus. This was where it starts to get a little confusing. So S is a binary function-only function that takes 2 function arguments. F is binary and G is unary. And what it does is it applies G to X and passes that as the second argument to the binary function F. And the first argument is just the original argument X. And one of the games that you can kind of play in your head is how many ways are there actually to combine a binary function and a unary function? All of those map to combinators. This is the S combinator where you apply a unary function to the left argument. If you apply it to the right argument, then it's the sigma combinator. If you apply two different unary functions, well, that's actually the phi combinator. If you apply g to both your arguments, but your arguments are different, that's the psi combinator. And then there's another one called the D2 combinator. But the point is like, you can think, how many different ways are there to combine a unary and binary function? All of these map to different combinators, some more useful than others. So I haven't listed all of them out exhaustively, but you can see that at the end of the day, these function-only functions and combinators are just various ways to compose these functions, one after the other. And we're going to see how we can use these. And I'm going to grab my water while we move to the next slide. So the rest of the talk is going to be working through a single example. If you've seen any of my YouTube videos on my code report channel, you'll see these kind of things where we do, 20 languages, one problem. Here we're going to do one problem, 8 languages. We're going to start off with Python, then go to Haskell, and then we're going to visit, I think, Clojure before we go on to live coding the array language solutions. So what's the problem? It's called special array, and the problem statement is the following. I'm not actually going to read through this because it's easier to see it by example. You're given a list of integers as your input, and you're going to return a true or false. You return true when the parity, another word for whether a number is odd or even, if the parity of every alternating element is different. So you return true when you have even, odd, even, odd, even, odd, even, odd. Every other case, whenever you have repeating odd elements or repeating even elements, you return false. Does that make sense? All right, I saw a bunch of nods. So we're going to walk through this example. We need to do two things first. The first thing we're really going to do in the examples is we're going to calculate whether they're odd. But because I want them to stay as numbers, we're going to do that second. The second thing, once we check whether they're odd, we want to compare adjacent elements. So we're going to take two elements adjacent at a time, and then we're going to compare these. The first thing we're going to do is we're going to convert them to whether it's odd or even, which is the equivalent of doing a modulus 2. And in array languages, we don't have trues and falses. That's just a 0 and 1, which is a lot nicer in certain cases. Then we're going to check, are these not equal to each other? Because we want them to be not equal in order to return true. So in every case except for the middle one, they are different. So we're going to get back true, false, true. And then in the functional world, you probably are all thinking you just do an and reduction, and that's going to give you back a 0 at the end of the day. Does that make sense? All right, everyone's nodding, fantastic. So we're going to move on to our first language. So these are all the languages that we're going to look at. It's showing, I think, actually 9. So I think that's because I added Clojure. Yes, but we're going to start with Python. And in Python, we only have idiomatically. Technically, you can define operators, but idiomatically in Python, you really only have functions for composing functions. So first, we're going to solve this problem. And this would be sort of the naive way you would do this. You've got a for loop, and you're looping through an index that goes up to n minus 1 because we're looking at adjacent elements. We can't do it for every I. It needs to be n minus 1, where n is the length. And then we have a simple if statement where we index into I and I plus 1. We do the modulus 2 to check whether it's even or odd. And if they're equal to each other, we short circuit and return false. Otherwise, if we get to the end of this loop and we haven't encountered any adjacent elements that don't have differing parities, we return true. So one of the first things we can do, because I hate this code, I just wrote it as a starting point, is I hate the indexing of having to index into I. So the first thing you can do to remove this is just by using a zip. So this is the zip tail trick that if you're a functional programmer, you're probably very familiar with. You zip a list with its tail, and then you can destructure with the iterable unpacking to get x and y. And so you've got the same structure, you're just avoiding the indices, which in my opinion is much nicer code. Now that you have this, though, you don't have any indices. The next thing I think is you don't actually need a for loop. We can turn this into a generator expression or a list comprehension. And that's the next thing we do. So we've got a function that takes this generator expression, does the exact same thing, we have no for loops, and as an array programmer, I don't like for loops at all, so this is much nicer code. But this is where Combinators comes in. So what do we have here? We have x modulus 2 not equal to y modulus 2. So we have the same unary function if we consider modulus 2. Modulus is a binary operation, but we're partially applying it with the constant 2. So a partially applied binary function is just a unary function that you could consider calling this odd. And then we're applying this unary function to two different arguments, and then taking the results of those and passing it to a binary function, in this case, not equal to. This is an example of the psi combinator. So I have a library called dovekey that provides both combinators and helper functions. So I've replaced the modulus 2 with a function called odd, which is our unary function. And then I've imported from the operator module ne, which is not equal, our binary function. And then psi is a combinator that applies a unary operation to two different arguments and then passes the results of that to a binary function. So odd's our unary function, ne not equal to is our binary function. And now because we have this, we don't actually need to do this destructuring in zip. We can pass this, and so this is psi, if you want to see the Python. I think we showed this on a previous slide. G is our unary function, applying it to both x and y, passing the results of that to f. And so this is psi. And this is, in BQN speak, what it looks like. So obviously this syntax, if you're not familiar with BQN, is going to look a lot different. The double struct capital F is our binary function. The double struct G is our unary function. The parentheses are unnecessary, but it might be more readable. Binary functions are infix here, so you can see we're applying G to our first argument and our second argument, the W and X, and then we just assign this to psi. So this is a way of implementing psi, but the big circle here, that is actually what psi looks like in BQN. That's the symbol for it. And we actually have this in Haskell. So it's called over. They don't use the combinatory logic names in array languages. But you have this if you're familiar with Haskell, there's a library called data.function, and you can import a function called on, which is their name for the psi combinator. So if we come back to this, we no longer need this zip. We can actually just use a variadic map now because we have a single function. We're not doing this modulus 2 with a not equal operation, and we can just pass this function to the variadic map, which is really nice in my opinion. So we started with that crazy for loop, indexing, all that stuff, and we've boiled it down to a single one-liner in Python, and I really, really prefer this code. It does come with the downside that you need to know what the psi combinator is, and arguably psi is not the best name for this. Maybe over on borrowing it from BQN or Haskell is better, but it's food for thought. So this brings us to our next language, which is Haskell, and Haskell has both functions and operators for function composition, idiomatically at least. And we're going to see this when we take a look at this solution. So, very different from our initial Python solution, but not super different from our final Python solution. You can see we have the map odd. Then we've got this absolutely inscrutable zip width not equal to angle star angle tail, and then a fold 1 ampersand, which is our and reduction. So what is this? You might be familiar with zip width. That's the zip tail trick that we saw using the slicing in Python. And the not equal to is spelled a little bit odd. Usually I'm used to seeing the exclamation mark equal to, but here it's a slash equal. But what is this angle star angle? That is the S combinator that we saw earlier, and that I said was a little bit odd, but it is fundamental. So what are we doing here? We're applying G, our unary function, to the right argument, and then passing that along with the original argument X to our binary function F. That's exactly what we need to do here. And this is called after in BQN, and it's also in J and I, two other array languages called hook. And you can see here, if that we come down to our table, we go to S, and we then go across to Haskell. You can see that there's actually two different ways to spell this. They have a function called app, which is short for applicative, and then we also have this operator. So if we come back here, what we're doing is our binary function is zip width not equal to. So we're applying this not equal to operation. So this is our binary operation. And the tail is the unary function. So this is just a very painful way of spelling our zip tail trick in Python, where we did the nums and then the nums where we dropped the first element. Some of you might be thinking, though, in Haskell, or maybe in a different language, there's a function that does exactly this. And that's the next modification. It's called map adjacent. You map a binary operation over adjacent elements. So implicit in this function map adjacent is this S combinator you can kind of think of, or maybe don't think of it, but it's good to know that these kinds of things, are behind the scenes. And I think this is much, much more readable, I hope you agree, than the previous solution. And on top of this, fold L1 ampersand ampersand is a really painful way of spelling the and reduction, which I would say unfortunately in Haskell is called and. Python called it all, I think that's a better name, but this is what they call it in Haskell. So this is what I consider like the best solution in Haskell. And it's curious to see that along the way we were using the S combinator. And the dots, these are just unary function composition. These are B combinators. So, last but not least, we can combine the map odd and the map adjacent into a single map adjacent by doing the exact same trick that we did in Python. So remember, we had the psi combinator, and we passed it the ne for not equal to and odd. We can do the exact same thing, except in Haskell, they call the psi combinator on. It's applying odd to each of the adjacent elements, and then the binary function afterwards. So I actually don't know. Like I just said that the other solution was the best. Is this one better? Once again, it requires you knowing what on does. That's one of the arguments against functional programming and libraries in general. The more that you use these, the more that you have to know them, and it requires your coworkers to know them. The point is, though, is that I'm just trying to show that this is possible, and these combinators can be very useful. So I think we're going to hop back to the Python solution. What we were missing from this to go to the next step was this map adjacent function. So we can implement that using a function from the itertools library called pairwise. Some of you that are more experienced Python developers, pairwise just gives you tuples of adjacent elements from a list or a string or something that's iterable. So if we have adjacent map, we can then plug this in, and now we don't even need to use the variadic map and the slicing. We can just make use of this thing that does exactly what we want. It's taking adjacent elements and applying a binary operation. And now we can actually get rid of the psi combinator. If we prefer, we can just map odd over our list initially and then pass the binary operation not equal to map adjacent. So we started off with a for loop. Then I showed you some fancy combinators, got to this, in my opinion, beautiful solution, but arguably it's using this random dove key library that uses the psi combinator. But then because we looked at another language, discovered an algorithm, the point is that by learning these combinators and algorithms, you can notice the connection and then choose which one you think is best. Arguably, this code is better. Everyone knows what map does. Everyone knows what odd does. You need to know any is short for not equal to, and you need to know what adjacent map does. But adjacent map, you might be able to guess what it does just based on what its name. Whereas psi, you're not going to guess at all, unless if you are versed in Haskell Curry's papers from the 1930s. So this is the next evolution of our Python solution. And at this point, it's going to bring us to Clojure. So Clojure is going to look a lot different. It's going to use the threading macro. And I'm not going to walk through this because we're running not short on time, but I want to get to the live coding. So just note that threading is kind of a different way to compose functions in sort of a modern Lisp, if you will. And I think I show an alternative way of solving this as well with two different versions of sort of lambdas. But that is going to bring us to our array languages and our live coding, which is going to be the remainder of this presentation. So APL, BQN, J, and cap, these are all array languages. They don't use functions for composition. They use the operators similar to what Haskell does, but then they also use these things called trains. So what are trains? Trains are just putting functions side by side, the juxtaposition of functions. So we have 2 trains and 3 trains, which, as you might imagine, 2 trains are when you put 2 functions side by side, 3 trains are when you put 3 functions side by side. Some people refer to these as invisible modifiers because there's actually no explicit syntax for composing. It's just the putting of these functions next to each other that forms the composition. And you can note that J, they chose for their 2-train S and D. I'm not going to talk about why, but the array languages later on decided that B and B1 were better. And interestingly, cap doesn't have a 3-train, at least in the train version. They do have the combinator, but it uses explicit syntax. So if we filter for the ones that correspond to the 2 and 3 trains in the array languages and we add phi1, these are the ones that correspond to our 2 trains and 3 trains. And I believe this brings us to our live coding. So hopefully we're going to have no hitches here. I think we're going to start with APL. And believe it or not, this is going to happen pretty quickly. So our example we're going to start with is 4316. That's the example. So the first thing we want to do is modulus 2. We're done. 2 pipe is how you spell modulus 2. If you saw Steven's talk, you'll know that implicit iteration comes for free, and you only need to write 2 characters. The next thing we want to do is we want to compare adjacent elements. So there's something called an n-wise reduction in APLs, where you specify an n, here 2, and that will then perform a reduction on each of that sliding window. So here the reduction is catenate, so that's just going to... Oh, where'd it go? The risks of live coding. Let's try that again. So here, if we use catenate, this just gives us, basically, it forms a list for each parent. If I change the 2 to 3, then I'm going to get lists of 3. And it's a sliding window, so each window steps by 1. But really what we want to do is we want to keep this as 2, and we want to change this binary operation to not equal to. If, oh no. There we go. Not equal to. So this gives us the 101, and after this, all we need to do is an AND reduction. And we're done. So, how do we turn this to a point-free expression? Because right now it's not point-free. If we try to do this, it's not going to work because it expects a 3 train or a fork at the beginning. So I don't have time to go through explicitly what a 3 train is, but note that here we've got basically a constant number, then a binary function, and it expects a unary function on the right here. So we just need to replace this with an identity, and now it'll parse correctly. So that's our dialog APL example. We're now going to switch to this editor, which you can see I was already practicing on. So we've got the same list, and this is just an alternative APL, but it doesn't have the 3 train. It doesn't expect forks. So the solution is the exact same. 2 pipe, and then we want to do the 2 catenate reduce just to show that you get your adjacent elements. Replace this with a not equal to, and then we want to do our and reduction at the end of the day. The difference now is that when we try to make this tacit, we don't need to change this at all. Because what ends up happening here is the 2 modulus, this forms a unary function. This 2y's reduction also forms a unary function. And this and reduction is also a unary function. And because they only have 2 trains, whenever you have unary functions next to each other, it's just the B combinator over and over again, which makes this a much easier language to understand. So if we evaluate this, we get 0. So that's our second array language. We're going to hop back here. I'm going to go control, fun, page down, and that's going to bring us to BQN. So we already saw BQN at the very beginning. We're back here. So what are we going to do? 2 modulus. And all of these editors that I'm showing you, this is all in the browser. So you can go, I'll show links at the end. If you want to go play around with this after this talk, you can just start typing. You don't have to download anything. So 2 modulus gives us our array of booleans, 0s and 1s. We then want to do, we actually don't have NY's reductions in BQN, so we have to do a 2 windows, which is going to give us, if we zoom out a tiny bit, it's going to give us basically a matrix of 2 elements in each row. And then with that, we can do a not equal to reduction on each of the rows, which is a longer way of spelling kind of the NY's reduction. And once we do that, we just need to do a andY's reduction, and reduction, which is going to look like the following, and we get our results. So to turn this into point-free, we have to do the same trick we did in dialog APL, where we put the identity here. But note that this does not give the right answer. We're expecting a 0 and a 1. What we need to do is we need to break up the forks here with something, it's literally called nothing, which is this little dot here. So that basically takes our forks, or what is expecting to be 2 forks, and turns it into unary function composition. So this basically enables you to change the combinator that you're spelling implicitly here. And I think that brings us to our last array solution from this set, which is going to be J. So J is an ASCII-based array language. It was basically APL 2.0. The inventor of APL, Ken Iverson, gave up on Unicode symbols and trying to evangelize them, and then he created an ASCII language afterwards. Devin, who's in the crowd, is a longtime J programmer. So that's your list. The next thing we do is 2 modulus. The next thing, and we're going to space this up a bit because it's kind of hard to read, is a 2 slash, and that's going to give you your adjacent. Here, we don't have the not equal to sign because that's a Unicode symbol. So the not equal to is a tilde colon, and then this is actually expecting a unary operation, so you don't get the reduction for free, so you need to put a slash in there. And if we do that, you get your 101. And now, once again, we don't have the set theory and, so we have to spell this with asterisks dot reduction, and that's your final answer. To turn this point free, it's pretty awful. First, you have to do identity, which is the left bracket, and then you need to do the equivalent of nothing in BQN, which is called cap. And actually, the cap goes over here, I believe. So this, obviously, a lot less beautiful from before. I'm going to hit enter, and hopefully it gives you the right answer. But yeah, tacit programming in J can be a pain. I think we're going to go back to the slides now. We're going to try and wind down in like the next 5 minutes here to leave time for a couple bit of questions. So we've got 2 more languages, Jelly and then Uiua. So Jelly is the one with chains, and Uiua is the one with stacks. But these ones are going to be pretty quick. So Jelly is actually a tool, or Jello is a tool that I wrote to decipher Jelly code. Because Jelly code is so confusing. It was designed with the sole goal of winning at code golfing, even for someone who loves all these esoteric languages, it's hard for me to understand. So Jello is a keywordified jelly. So I get to type functions, and then it'll convert them into the jelly code, so I don't need to understand jelly. So we've got our example. I here is just the I combinator. It gives you back what you input, so we just have our list. The first thing we want to do is mod 2. And note here that I have designed into it autocomplete, so you can discover functions pretty easily. So mod 2, one of the coolest things that I've built into this tool is that it gives you suggestions for things you might not know about. A different way for spelling mod 2 is odd. So I can just replace this with odd, and it gives you the exact same result. And after odd, you then want to do the not equal to prior. And once again, this is going to give us a suggestion. So you're checking whether adjacent elements are not equal to each other. There's actually this exact function in a language called Q called differ. And so we can replace this with differ. And then finally, we just want to do an and reduction, which is going to be an and fold. Once again, we have a shortcut for this, which is just all. So we can go back and replace that. And that's our full solution in Jello, which gets converted into jelly. So this yellow code on the left, that's the jelly code. And that reads B over dot D accent caron A under dot. So that's the jelly code that is actual language. It gets actually used. But as you can tell, that's completely inscrutable. What's interesting about this language, though, is the way that it works is they don't have overloaded arities for their functions. In all the array languages, every symbol has two meanings, a unary one and a binary one. So that limits what you can do with function composition. Jelly, every symbol only has either a monadic, a unary, or a dyadic, a binary definition, which means that it'll create something called an arity chain. That's that 1, 1, 1. And then it does this pattern matching. It says whenever you see two ones in a row, that's unary function composition. So if we go back to our initial full-blown where we did mod 2 not equal to prior and then and fold, and we zoom out a bit, first of all, you can see you get all your algorithm recommendations. But at the bottom, you get this much more complicated tree because the arity is 2, 0 because a constant has a 0 arity, 2q, 2q. The q is short for quick, which is what Jelly calls a higher order function. And so this shows how things combine, and at the end of the day, you still end up doing two B combinators, unary function composition, but it makes it so much easier to understand what this code is actually doing. Last but not least, we're going to go to Uiua, which I believe is here, and we're going to do this very quickly. First thing we want to do is mod 2. Note, Uiua also does not have overloaded monadic and dyadic definitions, so every symbol just has a single meaning, and you can just type what it is, and when you hit Control-Enter, it'll automatically convert it to the symbol. So this is actually an easier language to learn, if you will. We then have Windows 2 to do the same thing that BQN did. We then want to do a row-wise reduction of not equal to. And then once we've done this, we want to do a slash min, because there's actually no logical and here. So min is the same thing on the space of Booleans, and that is your Uiua solution. So I believe we're going to go back to our slides now. That's all the solutions. And it brings us sort of to the summary of this, is that in CAP, we have the following. B combinators, because you've just got unary function composition due to the fact that you don't have 3 trains. In APL, you've got the phi combinator, which is a 3 train, another 3 train, then a B combinator. Uiua, you don't actually have anything. You just get this for free because of the way stack languages work. So if you're interested in learning this stuff but aren't interested in the combinatory calculus stuff, you might want to check out Uiua. Then BQN, similar to Dialog APL, but because we don't have the n-wise reduction, we actually have to do this extra operation of the windows followed by the row-wise reduction. And then unfortunately, we have this nothing, which is very confusing. And I think you need it in a language like this, and it's sad that Dialog APL doesn't have it. But yeah, unfortunate that you have to switch what the combinators are happening implicitly here. Then in J, we've got phi, B, and even worse, like at least nothing is only an almost invisible single glyph. But in J, it's left bracket colon, and that's even more, ugly in my opinion. And then finally, in Jello, it reads left to right, B combinator. You might say that all of the top solutions, a little bit hard to read, maybe, but the bottom one is actually pretty straightforward. And I really like this code. This is a summary of all the different composition strategies that you have access to in these languages. And in conclusion, be curious. even if like I don't write in these in my day-to-day work at NVIDIA, but it helps inform the way that I'm designing libraries and languages in my research work, because there's a lot of interesting ideas here. I have a podcast, as I mentioned, Algorithms plus Data Structures equals Programs, the name we stole from a Nicholas Wirth textbook. But the more and more I learn about these array languages, the more and more I think that we should have named it Algorithms plus Combinators equals beautiful code. Like I said, this is kind of the summary of this talk. If you only take away one thing, even if you don't understand this table, just know in these different languages, whether it's Haskell or an array language, there's different strategies for these function composition techniques. And revisiting our first problem, we can actually get rid of all of this if we implement another function that the Q language had, differ. And you might be wondering, why is someone from NVIDIA so interested in all these languages? Differ and all is just a reduction. Differ and map are just maps. Maps and reductions are like the most easily parallelizable functions across any language. So code like this, as opposed to the code that we saw at the beginning with the for loops and the indices, is way, way easier to accelerate. If you want to check out any of these languages, as I mentioned before, those were all web editors that I was demoing and live coding with. You can check them out here. The GitHub repo has links as well, so you don't need to type this stuff out. These two libraries I wrote myself. They're complete to a certain extent, Dovekey in Python and Blackbird in C++. And if you want to check out anything more about combinatory logic, there's a website, combinatorylogic.com. Thank you.